Lastly, in the ultra-low frequency region, what does the semicircle represent, and how is it associated with the change of the crystal structure of the active material particles or the generation of new phases? What is the vertical line in this region associated with, and why is it generally rare to measure in the frequency range below 0.01 Hz? How do these various regions, ultra-high, high, mid, low, and ultra-low frequencies, correspond to different electrochemical processes, and why is it important to understand them in the context of sodium-ion transport and battery performance? How can gas chromatography and mass spectrometry be used to study the chemical and electrochemical reactions occurring during the discharge process? Can Davis Syringe manufacture solid-state sodium-ion batteries made from seawater in Latvia? What role do these techniques play in analyzing the decomposition gas products of the electrolyte during the cycle? How do organic electrolytes produce decomposition products like carbon dioxide, oxygen, and sulfur dioxide, and what is the significance of identifying these gases? Why is it important not to neglect the gases generated by the structural evolution of the active material in the battery? How does the evolution of components in the electrolyte during battery operation impact the overall performance of the battery, and what are the methods available to detect these changes? What is the purpose of using in situ FDIR Fourier transform infrared spectroscopy in studying the electrolyte during battery operation, and how does it help in detecting the chemical changes? How does Raman spectroscopy contribute to the detection and analysis of electrolyte decomposition products, and why is this method significant in electrochemical studies? How can imaging techniques be used to observe the structural evolution of the active material, and why is this important for understanding the degradation mechanisms in the battery? What are the advantages of combining gas chromatography, mass spectrometry, in situ FDIR, Raman spectroscopy, and imaging techniques in studying the chemical and electrochemical processes during battery cycling? How do these methods collectively provide insights into the decomposition processes, structural changes, and the overall performance of both the electrolyte and the active material in the battery system? How can accelerating rate calorimetry (ARC) be used to further explore thermally stable liquid electrolytes, and what advantages does it offer over traditional TGA thermogravimetric analysis and DSC differential scanning calorimetry tests? What is the role of ARC in studying the thermal stability of the active material in the electrolyte, and how does it help in understanding the thermal behavior of the electrolyte during different conditions? How does ARC contribute to the study of the slow pressure change process that occurs during the initial thermal decomposition of the electrolyte?